Hello everyone, welcome back. Chapter 5, General Chemistry, Chemical Kinetics. This is a very quick chapter. We'll go through it relatively fast because the scope to which the MCAT can ask you about this is limited in the general chemistry fashion, but it gets a little more complicated when we get to organic chemistry. We start talking about thermodynamic and kinetic control of chemical processes. We talk about catalysts and this and that, whatever it is. There are a lot of Anki cards that float around there about chemical reactions and rate orders and which graphs correspond to which rate orders and everything, blah, blah, blah. If you are someone who can mathematically think through that and understand it, go for it. I, unfortunately, in my undergraduate studies, never dedicated the time to understand why each of those are derived the way that they are. So it sort of flew over the wayside. And to this day, I don't exactly know why each rate order or rate law looks the way that it does. But I'll do my best in explaining it to you. And the bare minimum understanding that I have of this that got me a perfect score on the MCAT in this section. So hopefully it translates over. Although I know that the exam changes year to year, so go by what the most recent sort of information is. This is really a baseline for you. And as you continue on and you do your own studies and you make something of yourself in the realm of the MCAT, just make sure that you keep up to date with what's happening. Okay? All right. Let's do a quick chapter, something easy. Chemical kinetics. Basically, we need to talk about one thing called spontaneity. Can't spell it, so just pretend I can. Does anyone else have a marker? This one's dying on me. Huh? That'd be fine if it shows up properly. Yeah, that's perfect. Let's just show up on camera. Yeah, that'd be great.
That shows up.
That's fine. Okay, perfect. We've now harvested the markers from the room. You know what's funny? Like, I remember when I woke up this morning, I was getting ready for prayer, and I saw on my table the markers were there, and I was like, yeah, I'll grab them before I leave the house, 100%. Like, I won't forget that. Here we are. Oh, well. So sad. My depth perception, again, it was you, right?
Yeah.
I have really, really bad depth perception. I think I need glasses, to be honest. I scheduled with an ophthalmologist because I have a crazy astigmatism when I drive at night, number one. Number two, and this is like the horror story that like everyone who gets glasses starts telling this story, it's taking me longer to focus between focal points. So like I look at something further away, and it takes me like a fraction of a second longer to focus. That's what med school does. I told you guys I have like tendonitis in my hand, like there's this like little permanent scar on my hand from taking so many notes. While I was studying for step 2, I took so many notes for so many hours that I developed like tendonitis in this part of my hand, and now there's this permanent little hard scar on my tendon. Yeah? Battle wounds. The spontaneity of a chemical reaction basically is dictated by something known as the Gibbs free energy. Basically, the spontaneity means what? Who can define spontaneity for me? Whether or not a reaction will happen without an input of energy, right? Is it faint?
Yeah.
A little bit? Okay. So the spontaneity basically means, will it happen? Someone go hunt down a marker for someone hunt down a black marker. Let's see it. Will it happen? There we go. Without input of outside energy. If the answer is yes, it's spontaneous. If the answer is no, it's not spontaneous. And basically, this entire trend of spontaneity versus inspontaneity is determined by the Gibbs free energy. Spontaneity is not equal to speed. Have you guys seen that video on YouTube of that physics professor who like holds the bowling ball to his face and lets it go and like comes back up? The way he says speed always gets me. He's like, if I don't succeed at giving this 0 speed, you guys know the video I'm talking about, right? All right, let's see how niche your guys' YouTube knowledge is. Have you guys seen the video of turning a sphere inside out? Like the topology video, that mathematical like topology video? Okay, that's too niche. All right, let's see where you guys are at. Have you guys seen Vsauce's video about like linguistics? like how language is formed over time and like things like that. Yeah, you have? Yeah. Who here is big on like video essays? Like watching like an hour and a half of just someone talking about some niche subject. Who has watched the one of why SpongeBob SquarePants is the greatest show of all time? Everyone go watch that video. It's a really good video. It's like a thesis and then antithesis, and it creates this beautiful metaphor of like why the writers of SpongeBob did something so incredible like in the early mid-seasons of the show. Really good. If you guys want something to watch like when you're eating food, look up this YouTube channel, Nexpo. The Nightmare Expo. Oh my God, so good. What an incredible YouTube channel. The guy's killing it. It's like horror stuff. If you guys are into like horror movies and scary like cult stuff. Oh, there's one video you should watch. This is completely off topic, but whatever. The Cult at a Boarding School.
I watched that one.
You guys watch this tonight. You know what? Click off this video, take a break, and watch this. The Cult at a Boarding School. Go get something to eat, finish watching this, and then come back and learn about chemical kinetics. That's your homework. Everyone go home. All right. Great video. What a fantastic video. That and Searching for the Five. Really, really great videos by Nexpo. So spontaneous is not equal speed. And this is proven to us because one of the spontaneous reactions that we actually see in the world naturally is rusting. The rusting of iron is something that's actually spontaneous. You don't need to put in outside energy to make it happen. But iron rusts very slowly. Happens very slowly, right? So spontaneity doesn't equal speed. And there are reaction mechanisms that we need to talk about. This understanding of reaction mechanisms is the fact that reactions happen in stepwise fashions, or stepwise fashion, that adds up to a total reaction. A2B, A2 plus B yields A2B. A2B plus B yields 2AB. So the total reaction here is going to be A2 plus 2B plus A2B yields A2B plus 2AB. And we see A2B on this side and on that side, so that means we can cancel it out. And by canceling it out, we can actually just erase it, right? And that's going to be our total reaction. A2 plus 2B yields 2AB. So we can see this piecewise fashion by which it happens, right? Now this A2B is known as what? It was made in the reaction and then used in the reaction later to make the product. That is called a intermediate. So an intermediate is a molecular species formed within one of the steps of a reaction and later used to push the reaction forward. Now, notice I didn't say that it disappears, because sometimes you can have a product that is also an intermediate to another part of the reaction. So you can isolate both. You can have an intermediate that is a primary or secondary product of the reaction that also leads to formation of another product. What's an example of that? Let's say that in an aldol condensation, you are trying to isolate this. That's what you're trying to, Orgo people who have not taken Orgo or don't know Orgo that well or don't like Orgo, tune out for a second. Aldol condensation, you want to isolate this. In the process, you need to make what? My people who like Orgo, you know you need to make this in the process from this. So this to that and that to that, this is your primary product. And this was the product of the initial reaction, but it becomes an intermediate in the overall scheme. The product also serves as an intermediate. Make sense? This is known as the beta hydroxyaldehyde. This is the alpha beta unsaturated aldehyde from the aldol reaction with NaOH and an acid wash. Overexposure is a beautiful thing in education. If you have a teacher who overteaches your class, they really care about your future. Because the thing is, like, you will eventually hit a point where you just like get all of these terms slammed at you, and your body just wants to like shut down and like be paralyzed. But if you're just like spoon-fed it like little by little by little, you're like, oh, I've seen that before. That's not so crazy, right? Just tiny bit at a time.
You want to start glycolysis now?
Yeah, man. I mean, forget glycolysis. We're going straight to gluconeogenesis. Where are the two sites that gluconeogenesis happens in the body? 90% of it happens in the liver. Another 10% in the? Yes, very good. In the kidneys. There is a theory of chemical kinetics known as the collision theory. Very easy to understand. I'm not even going to write notes about it. More molecules at faster speeds means more collisions, means more effective collisions, means more reaction. That's it. But one thing we need to elaborate on is what defines an effective collision. Anyone? Anyone to crack at that? What defines an effective collision?
More reactants? More reactants?
Not so much as like what will make for an effective collision. So the answer given was more reactants, and that will make for a more effective collision because you have more opportunity for those reactants to collide in the proper way. But what do I mean by the proper way? That's what I'm asking. The orientation, yes, but the collision, if they collide at a slow speed at the right orientation, will the reaction happen? Probably not. So what makes for an effective collision? What defines? What is the cornerstone of effective collision? It will lead to what? Huh? Over there in the back. What'd you say? Energy? What type of energy? Activation energy. An effective collision of reactions should lead to the necessary activation energy of the reaction being reached. So let's talk about that for a second. Is that what you said? Yeah? Okay. Good. Let's talk about a reaction diagram for a moment. We have a reaction coordinate. This is time. This is the relative energy. I guess you could leave this unlabeled for a moment. It could be enthalpy, it could be Gibbs free energy, all of that stuff, right? Every reaction diagram is going to look like one of two things. Like that. Or like that. This is called exothermic and endothermic. Wrong. Because I didn't label the axes. If this was delta H, or I just say the enthalpy of the reactants is greater than the enthalpy of the products, that means that the delta H is positive. Sorry, my bad. The delta H is negative. You have this, you're losing H. Delta H is negative, correct? So we go from like 100 to like 50. So that delta H is negative, we would call that exothermic, right? And this would be endothermic. But what is it when it's delta G? Exergonic and endergonic, correct? Someone double check me on that. On the delta H portion, it is exothermic, correct? The one thing I never understood about the delta, someone look it up anyways, just to put my mind at ease. The one thing I never understood is why is it called thermic if it has nothing to do with like temperature, but then again, temperature is just like average kinetic energy, and this is like heat energy being transferred. Just trip me up.
Yeah,
so
that's the way I understand
if it was enthalpy, it would be thermic, and then if it's delta G, if it's Gibbs free energy, it would be gonic. So a spontaneous reaction is also known as exergonic, right? So let's do that on the board. Exothermic equals negative delta H. Endothermic equals positive delta H. Exergonic equals negative delta G, which means spontaneous. And endergonic equals positive delta G, means non-spontaneous. We will have an entire chapter dedicated to thermodynamics. That will be a very difficult chapter, but we'll get through it. So the effective collision is dependent upon, do you get enough energy within the collision to form the transition state? Let's look at the overall reaction real quick with a G, a Gibbs free energy. The change in the Gibbs free energy is shown over time. Yes? And if we were to look at that reaction, up here would be something known as the transition state. That is the symbol for a transition state. It is not this. It is this. Notice it's a bit longer, and it's a straight line coming down. This is not equal to this. Let's talk about transition states. We have A2 plus 2B yields 2AB. There's two ways that this transition state can kind of look. We can have something known as an early transition state, and we can have something known as a late transition state. I'm going to draw this over here. In the end, we need it to look like this, right? Yes? How are we going to do that? If we have an early transition state just means it resembles the reactants more. And a late transition state means it resembles the products more. So let's do an early transition state first. So the bond between A and A will still be relatively strong. Oops. And the bond between A and B will be relatively weak. Because in the reactants, there is no bond between A and B. So there's a weak bond between them in the early transition state. Do you guys get that? We show a transition state by bracketing and putting that symbol. And then the reaction will go on and finish and give you that. A late transition state will look more like the products. So the bond between A and A is now very loose because it is absent in the products. And the bond between A and B is stronger because it is present in the products. Do you guys get that? Do you guys see the difference? Question is, which one's which? If we look at our reaction diagram again, mini reaction diagram, what do you guys think is early and late? Just look at the time coordinate and where the transition state is. This exothermic or exergonic reaction has an early transition state. This endothermic or endergonic reaction has a late transition state. Understood? But which one are you going to use for the transition state? I opt to use the endergonic, exergonic thing because it's showing you the whole reaction coordinate and the spontaneity of it itself, right?
Wait, so is like the time of the transition state associated with like it being endergonic or exergonic?
Yes. So something that's going to have, a more, the question was the timing of the transition state, is that related to the fact that it's endergonic or exergonic? Yes, that's why I put those up on the board, right? I am pretty sure that it's related to delta G more than delta H, but you guys could double check me on that and come back to me with an answer. Yes?
Could you explain the early diagram again?
Yeah, so basically, we get to our activation energy early and then we drop down. Because there's a very small hill to climb, right? This is the activation energy right here. Whereas if we have a much higher hill to climb, it's going to take us more time. So this is the activation energy, and the higher activation energy means it's going to take us more time. It's a later transition state.
In that, the diagram with the A's and the B's,
This is early because the bond here is stronger like it is in the reactants.
yeah.
And this is late because the bond here is stronger like it is in the products.
Okay.
Because the products are the late part and the reactants are the early part.
But in the reactants, aren't there like two B's that are, never mind.
They're not so two B's bonded together would be B2. I specifically wrote 2B. Very different. But I'm glad you asked. How are you feeling? That's a good sign. I feel great. I'll answer for all of you. Keep going. Keep teaching. Keep us here all night. No, I won't do that. I might. Someday. So we did free energy diagrams. We did exergonic, endergonic. Transition state is the peak of the energy diagram, blah, blah, blah. What affects reaction rate? What time is it?
6:40.
Ooh, I said you'd be home by 6:45. I lied. I do that a little bit every now and again. Not because I hate you, but because I care about your academic success, for whatever reason. Rate is affected by what? Temperature. That's what everyone knows. Higher temperature means, bless you, higher average kinetic energy means more effective collision. X bar means average. Temperature is just a measure of average kinetic energy. Because when something has a specific temperature, let's say this is a kinetic energy, the temperature of the sample is associated with kinetic energy that's right here. The kinetic energy of the whole thing would actually be a little bell curve like this. Right? A little bell curve like that. Most of them are there, but some of them are at the extremes, right? Average kinetic energy gives you temperature. We used to make a joke when we were walking around New York in the middle of the winter, right? We were like, somewhere in this very cold air, there is a molecule zooming around with a lot of kinetic energy, and it's just getting thrown into the average. I hope that molecule comes and hits me, and I feel it. I feel the warmth of that single molecule on my face. As you can see, I was always a loser. I was always boring. Not anymore, though, right? Yeah. You don't have to answer that. Obviously, reaction concentrations, like our buddy said before, So this is what he was getting at. I think this is what he had in mind. That when Benji told us, he said, the number of reactants will influence the effective number of collisions. It's correct that it'll influence the rate. The rate of the reaction is picked up by more reactant. Because basically, imagine you want people to bump into one another. Is that going to be easier in Tulsa, Oklahoma, or is that going to be easier in Times Square, Manhattan? Right? The solvent makes a difference. If your solvent stabilizes the transition state, it will greatly speed up the reaction. And the last thing is catalysts. Catalysts will lower the activation energy of the complex, making it easier to reach the transition state. Uncatalyzed. Catalyzed. Lower energy hill to climb means easier to reach there, means easier to go back down the hill and give you the product. Let's talk about reaction rates. So the rate of a reaction is actually dependent on a couple things. AA plus BB yields CC plus DD. The rate of this reaction is equal to the concentration of A to the power of A multiplied by the concentration of B to the power of B. Oh, sorry, not A and B, my bad. A to the power of X and B to the power of Y. I was thinking about equilibrium for a second. Very different. Very different. Equilibrium does not connect with rate. Why? I have a forward arrow here. A forward arrow. Not an equilibrium arrow, not a resonant arrow, not an electron arrow, not an arrow going straight into my head and putting me out of my misery. This is a reaction arrow. Okay, Robin Hood. What's that game? I took an arrow to the knee. Is that Skyrim? Skyrim, yeah. X and Y are the orders of A and B with respect to the rate. I don't really want to explain what that means. I just want to tell you what question it answers. It answers the question of, by what factor, by what exponential factor does a shift in that particular reactant concentration due to the rate of reaction? By what exponential factor does a shift in that particular reactant concentration due to the rate of the reaction? And there is one thing I'm hiding from you. What is the thing that I'm hiding? It can't just be this. There has to be a constant. And that constant is known as K. It's called the rate constant. Now it's an equation. Because before it was just a proportion. And to turn a proportion into an equation, you add a constant. So for example, a very famous physics example of that is that the energy of material is proportional to, I can't do this. There you go. Proportional to its mass. To make this an equation, you add a constant and make it equal. The force of electrostatic attraction is proportional to Q1, Q2 over R squared. Throw a K in there. And now you got equal. Right? Same thing with the force of gravitational attraction. Is equal to, or proportional to, M1, M2 over R squared. Throw a G in there. Yeah, that's how science works. You do so many of those calculations that you estimate the constant and then throw it in there. Then it becomes a law. Did you notice that those two equations I just put on the board are the same thing, but for subatomic particles and huge planets? Oh. Wow. We're getting somewhere. K is affected by what? Temperature only. This is the K constant at a specific temperature. It will be different at 21, then 30, then 45, then 57, then 600 billion quadrillion on the surface of the sun, right? Let's toss the iPad for a second. MCAT people, who's taking the MCAT before? What do questions look like about rate on the MCAT? They gave you a big table. They give you a big fat table. All right. Here's what the questions will actually look like for you. They will tell you that you have an equation. A is going to react with B and give you C. And they will give you a big fat table. And this is going to be a lot simpler than what you actually see. I'm going to be nice. And I'm going to ask you to figure out who's not going to be so nice. They will give you the concentration of A, the concentration of B, and the rate. And they will say, trial 1, trial 2, anyone traumatized yet? Trial 3, and trial 4. Yes, looks familiar? Anyone? Concentration of A is 4, concentration of B is 5, the rate is K. Concentration of A is 8, B is 5, K is 4K. Concentration of A is 8, B is 10, 4K. Concentration of A is 2, B is 5, rate is K over 2. And they will tell you, given this, what are the relative values of X and Y? Anyone? What's the value of X? 2. It's the easy one, right? Why? Well, we doubled A and kept B the same, and K went up by 4. That's 2 squared. Ooh. Sorry. And when I took A and I halved it, I went down by a quarter. I made a mistake. Went down by a quarter. That's what it's going to look like, right? But what is the more important thing is, what is y? 0. Because b does not have an effect on the rate. Changing the concentration of b does not have an effect on the rate. Now, let's do another one. Same thing, same number of trials, but let's do it with numbers. All right. I'm going to ask you guys to not freak out when you see it, because this is kind of how it's going to look on the MCAT, and I just want to get you ready for what you're going to see. Two, 6, 2, 1. 2, 2, 4, 2. (1.2 times 10 to the negative fifth) Now I'm screwing myself. I got to do this math myself. 3.6 times 10 to the negative fifth. (4.8 times 10 to the negative fifth). (6.0 times 10 to the negative sixth). Let's work through this together. Take your standard with the easiest to work with numbers and make that your point of reference. When I tripled A, I did what to the rate? I tripled it. So it's looking like the rate order of A with respect to the rate is 1. Let's see if that's true. Is there any other place that I manipulate A without touching B? Yeah. So I cut A in half, and I cut the rate in half. So it looks like x is equal to 1. Because whatever I did to A, that's what happened to the rate. 1 to 1. Make sense? What about this guy? I didn't touch A. I doubled B. Rate went 4x, which means that y is equal to 2. Because when I doubled it, I squared that that effect of the double, and it made 4. You guys get that? So if we were to write a full rate equation for this, it would be rate equals k a b squared. You guys get that? Does that make sense? Does it make sense with the numbers? Yeah? It's the end of the chapter. That's it. Any questions before we adjourn? Thank you guys so much for watching. Please check out the description below to support the channel, and I'll see you in the next one.